Namaste students. In the last class we were studying about singular and non-singular matrices. So a square matrix A is said to be singular if determinant A is equal to 0. A square matrix A is said to be non-singular if determinant A is not equal to 0. Then I have told one important property. If A and B are non-singular matrices of the same order, then AB and BA are also non-singular matrices of the same order. We have discussed with that. Now in this class we are going to study two important theorems and then we move on to the problems. Here we have to note that if A is any square matrix, if A is any square matrix of order 3, then determinant of adjoint A is equal to determinant A square. We have to prove this. This is the important theorem. If A is any square matrix of order 3, then determinant of adjoint A is determinant A the whole square. Remember, I take up the proof now. We have A into adjoint A is equal to determinant A into I. That's what we have. Now, A into adjoint A will be, what is this? Determinant A 0, 0, 0 determinant A 0, 0, 0 determinant A. That's what we have got. If you take the determinant throughout, what happens if you take determinant throughout? Determinant A 0, 0, 0 determinant A 0, 0, 0 determinant A. Now, you know this, determinant of product of two matrices is product of their determinants. Let us take determinant A as common factor from first row, determinant A as common factor from second row, determinant A as common factor from the third row. You will be getting 1, 0, 0, 0, 1, 0, 0, 0. I think you have understood this. Determinant A into adjoint, determinant of adjoint A is determinant A the whole cube into 1. What is the determinant of identity matrix? It is always equal to 1. So 1 determinant A cancels. You will be getting determinant of adjoint A is equal to determinant A the whole square. So 1 cancels. Hence we have proved determinant of adjoint A is equal to determinant A the whole square. I think you have understood how to solve this. Now let us generalize this. If A is a square matrix, if A is a square matrix of order n, then remember, here we have taken the square matrix of order 3. Now let us consider square matrix of order n, then determinant of adjoint A is always equal to determinant A power n minus 1. You have to remember this. Remember, determinant of adjoint A is always determinant A power n minus 1. So this formula is used to find out the determinant of adjoint without finding the adjoint. That's important. So you have to remember determinant of adjoint A is determinant A power n minus 1. Even the determinant of matrix of cofactors is also determinant A power n minus 1. You have to remember this. So both are important. So if generally you remember, if A is any square matrix of order n, then determinant of adjoint A is always equal to determinant A power n minus 1. I think you have understood this important property. Now let us take up another important theorem. I take theorem 4. It is given a square matrix A is invertible if and only if A is a non-singular matrix. Please look at the statement. If a square matrix A is invertible if and only if A is non-singular matrix. Write down the statement. A square matrix A is invertible invertible if and only if A is non-singular. A is non-singular matrix. This is the statement. A square matrix A is said to be invertible if and only if A is a non-singular matrix. That's what we have. So let us take case 1. Now a square matrix is said to be non-singular, then you have to prove that it is if and only if A is a non-singular matrix. Remember students, A is said to be non-singular. Let us take case 1. We know that AB is equal to BA is equal to I. You know this property? AB is equal to BA is equal to I. If A is in a square matrix, then there exists another matrix, square matrix B, such that AB is equal to BA is equal to I, then A is said to be the inverse of B and B is said to be the inverse of A. B is denoted by A inverse and A is denoted by B inverse. You know this property. Let us take determinant AB is equal to I. Let us take the determinant on both sides. Determinant AB is equal to determinant I. So, determinant A into determinant B is equal to I. Determinant of identity matrix is always equal to 1. You know the property, determinant of the product of two matrices is always equal to product of the determinants. Hence, determinant of AB can be written as determinant A into determinant B, and you know determinant of the identity matrix is always 1. Hence, you get determinant A into determinant B is equal to 1. So, since determinant A into determinant B is 1, we obviously conclude that determinant A is not equal to 0. Hence, A is non-singular. That's what the important note you get. I think you have understood this. See, first we have considered A is invertible. Since A is invertible, AB is equal to BA is equal to I, in which we consider AB as I. You take determinant on both sides. Determinant AB is equal to determinant I. Determinant AB is determinant A into determinant B is equal to determinant I is 1. So, since product of two determinants is 1, either of them is not equal to 0. Hence, determinant A is not equal to 0. Hence, we have concluded that A is non-singular. We have considered A is invertible and proved that A is non-singular. Let us take case 2, very, very important. Let us take data. A is non-singular. A is non-singular matrix means, what is the condition? Determinant A is not equal to 0. What to prove that? We have to prove that A is invertible. We have to prove that A is invertible. That means inverse of A exists. Let us take the proof here. What is the proof? We know that A into adjoint A is equal to adjoint A into A is equal to determinant A into I. That's what you do. You have this property which you have proved in the last class. Let us divide throughout by determinant A. What happens when you divide throughout by determinant A? A into adjoint A by determinant A is equal to adjoint A into A divided by determinant A. Let us take it for this. When you divide both sides by determinant A, what happens on the RHS? Determinant A cancels, we are left with I. Okay? So, how it is? It is of the form A into A inverse is equal to A inverse into A is equal to I, since the product is I. So, we have already told that it is of the form AB is equal to BA is equal to I. Then B is the inverse of A. Now, you compare this. When you compare this, A inverse will be equal to adjoint A divided by determinant A. Since determinant A is not equal to 0, we conclude A inverse exists. That is, A is said to be invertible. I think you have understood. Here we have the formula to find out the inverse. What is inverse? Inverse is given by 1 by determinant A into adjoint A. So first of all, A should be non-singular. That is, determinant A should not be equal to 0. Then you have to find out the adjoint. Then multiply adjoint of the matrix by 1 by determinant A. You will be getting A inverse. That is invertible. Think you have understood. So please understand this theorem. A square matrix A is invertible if and only if A is non-singular matrix. What is case 1? Case 1 we have considered data. A is invertible. When A is invertible, there exists a square matrix B such that AB is equal to I. We took determinant on both sides. Determinant AB will be determinant A into determinant B. Determinant of identity matrix is 1. So since the product is 1, either of them is not equal to 0. Hence we have concluded determinant A is not equal to 0. So inferring that A is non-singular. Then case 2, data A is non-singular matrix. So determinant A is not equal to 0. Then to prove that A is invertible. So we have used this property which we have proved in the earlier class. A into adjoint A is equal to adjoint A into A is equal to determinant A into I. You divide throughout by determinant A into adjoint A by determinant A, adjoint A by determinant A into A is equal to determinant A cancels, we are left with I. So you compare this with AB is equal to BA is equal to I. So we get A inverse, A into A inverse is equal to A inverse into A is equal to I. When we compare, A inverse will be 1 by determinant A into adjoint A. See, if determinant A becomes 0, then A inverse adjoint A by 0, it is not defined. So it exists only when A is non-singular. We have few properties, students. Remember, inverse exists only for non-singular matrices. First important property. Inverse exists only for the non-singular matrices. In the matrices chapter, we have seen that some of the matrices do not have the inverse. When we solved it using elementary row operation, so you have solved that A is equal to I into A and conducted series of row operation. For few matrices, I think you remember that inverse did not exist. Why inverse did not exist means the main reason is the given matrix A was singular. If you take the determinant of that particular matrix, the determinant A would have become 0. That's why inverse was not existing. So we conclude that inverse exists only for the non-singular matrices. Second important property, if the inverse exists, it is always said to be unique. That means one matrix will have only one inverse. One square matrix will have only one inverse. We cannot have two inverses for a square matrix, a theorem which we have proved earlier. And always remember, AB whole inverse is always equal to B inverse into A inverse. That means this is called as a reversal of inverses. Again, we have proved it in the matrices chapter. And always remember, A inverse of whole inverse is always equal to A itself. Suppose A inverse is given. If you take the inverse of A inverse, that will be equal to A itself, the square matrix itself. Always remember, you have already proved that A into A inverse is always I. Suppose if you take the determinant throughout, what happens? Determinant A into determinant A inverse is determinant of I is 1. Then from this we can infer that determinant A inverse is 1 by determinant A. So determinant of A inverse is 1 by determinant A. One of the important properties, it has been asked in the board examination once for 1 mark. So if A is a square matrix of order 2, then what is determinant of A inverse? That's what asked. So this is the proof. A into A inverse is I. If you take the determinant on both sides, determinant of A into A inverse is equal to determinant I. So we can use this property. Determinant of product of two matrices is always equal to product of the determinants. Determinant A into determinant A inverse is equal to determinant of I is 1. So cross multiply determinant A. So determinant of A inverse is 1 by determinant A. So that's what the property we have got. So I think you have understood this. This is the formula used to find out the inverse, remember. So I think you have understood. A square matrix A is invertible if and only if A is a non-singular matrix. That is, if A is invertible, then A should be non-singular. Conversely, if A is non-singular, then A is invertible. So both are possible. I think you have understood. An important note I have told you. All these are important concepts. Now, let us take up a few problems. It is given exercise 4.5. Find the adjoint in each of the following matrices. So, first matrix it is given 1, 2, 3, 4. Already I have done this. To calculate A11, cofactor of 1 is 4. Cofactor of 2, A12 minus 3. A21, cofactor of 3, it is minus 2. A22, cofactor of 4 is 1. What is cofactor of the matrix A now? 4 minus 3 minus 2, 1. What is the adjoint of the square matrix? It is transpose of the matrix of cofactors. Hence 4 minus 2 minus 3, 1. I think you have understood how to find out the adjoint. Interchange the diagonal elements, change the signs of the other elements. Similarly, we have got one more. 2 minus 3 minus 4, 6. Minus 4 minus 6. Very simple. You calculate A11 now. A11 cofactor of 2 minus 6. To take up A12, sign is minus. Leave the round column, we will be getting minus 4, minus of minus plus 4. A21, sign is minus. Cofactor of minus 4, minus 3, it is plus 3. A22, cofactor of minus 6, the sign is plus, it is 2. What is cofactor of the matrix? What is cofactor of the matrix? Find out cofactor. Minus 6, 4, 3, 2. Now what happens? Adjoint of the square matrix, we will be getting minus 6, 3 and minus 6, 3 and 4, 2. See, is it possible to get it directly? Yes. Interchange the diagonal elements, minus 6, 2 and change the signs of the other elements, 4, 3. Let us take A into adjoint A. A into adjoint A. What is A now? A is 2 minus 3 minus 4 minus 6. What is adjoint? Minus 6, 3, 4, 2. You take the product, 2 into minus 6 minus 12, minus 12. 3, 6, minus 6. Second row, minus plus 24, minus 24. Minus 12, minus 12. Minus 24, 0, 0, minus 24. That's what we have got. This is done. Let us find out. Suppose if we are taking it as A, let us take determinant A. What is determinant A for that? 2 minus 3 minus 4 minus 6. You will be getting minus 12 minus 2. It's minus 24. What is determinant A into I? Minus 24 into I is 1001, which is minus 24, 0, 0 minus 24. Call this as 2. So hence we get A into adjoint A is equal to determinant A into I. Similarly, we can prove adjoint A into A is equal to determinant A into I. For this problem, they have asked us to verify this property. A into adjoint A is equal to adjoint A into A is equal to determinant A into I. Think you have understood? Given a square matrix of order 2, you can get the answer directly by interchanging the diagonal elements and changing the signs of the other elements. So here we have taken adjoint A, then take A into adjoint A. We have got matrix A and adjoint A, you multiply that, you will be getting minus 24, 0, 0, minus 24. Then take determinant A, it is minus 24. Take determinant A into I, minus 24, 0, 0, minus 24. When you compare those two, you will be getting A into adjoint A is equal to determinant A into I. Similarly, we can prove adjoint A into A is equal to determinant A into I. I think you have understood the first two problems. Here we have discussed with 2 cross 2. Let us solve two problems on 3 cross 3. Given second problem, let us call it as A. 1 minus 1, 2, 2, 3, 5, minus 2, 0, 1. We have to find out the adjoint of 3 cross 3. It's very simple. Let us take A11, sign is plus, leave that row on column, 3501, which is 3 minus 0 is equal to 3. To take up A12, it's minus, leave that row on column, 2, 5 minus 2, 1. What is that? 2 plus 10, it's equal to minus 12. Think you have understood? 2 minus of minus 2. I take A13, the sign is plus, leave that row on column, 2, 3 minus 2, 0, 0 minus of minus 6, it is plus 6. Now let us take A21. A21 sign is minus, A21 minus 1, 2, 0, 1. Minus of minus 1 minus 0, it is plus 1. A22, it is positive. The cofactor of 3, leave that row on column, 1, 2 minus 2, 1. 1, 2 minus 2, 1, you will be getting 1 plus 4, which is equal to 5. I take A23, sign is negative. If you know the rule of signs, 2 plus 3, 5, sum is odd. So cofactor of 5, leave that row on column, 1 minus 1 minus 2, 0. 1 minus 1 minus 2, 0. We will be getting 0 minus 2, which is equal to plus 2. Now, I take up A31. A31, the sign is plus, the cofactor of minus 2, leave that row on column, minus 1, 2, 3, 5, minus 1, 2, 3, 5, which is minus 5, minus 6, minus 11. I take up A32, the sign is negative. If we want it for 0, leave that row on column, 1, 2, 2, 5, 1, 2, 2, 5, it is minus of 5 minus 4, which is equal to minus 1. To take up A33, sign is positive, leave that row on column, 1 minus 1, 2, 3, 1 minus 1, 2, 3, you will be getting 3 plus 2, it's equal to 5. So, I take cofactor of matrix A. What is cofactor? Write it in order. So, 3 minus 12, 6, 3 minus 12, 6, 1, 5, 2, 1, 5, 2, the third row minus 11, minus 1, 5. You want adjoint of the matrix A. This is got by taking the transpose of the matrix of cofactors, which is 3, 1, minus 11, minus 12, 5, minus 1, 6, 2 and 5. This is the adjoint of the matrix. So you have understood how to solve, how to find out the adjoint. We have one more problem. Fourth one. A is equal to 1 minus 1, 2, 3, 0 minus 2, 1, 0, 3. We want adjoint of this square matrix. You know how to find out the adjoint? Find out A11. Sign is plus, leave that row on column, 0 minus 2, 0, 3. Answer is 0 minus 0, 0. A12, sign is minus, leave the row on column in which minus 1 is present, 3 minus 2, 1, 3, minus of 9 plus 2, it is equal to minus 11. I take up A13, the sign is plus, that is cofactor of 2 you want, leave that row on column, 3, 0, 1, 0. 0 minus 0, it is equal to 0. I take up A21, sign is negative, the cofactor of 3 you want, minus 1, 2, 0, 3, minus 1, 2, 0, 3, minus of minus 3, minus 0, it is equal to plus 3. I take up A22, the sign is plus, you want the cofactor of 0 here, leave that row on column, 1, 2, 1, 3 we get, 1, 2, 1, 3. What is the answer? 3 minus 2, which is equal to 1. I take up A2, 3, the sign is negative, you want cofactor of minus 2. Leave that round column, 1 minus 1, 1, 0. 1 minus 1, 1, 0, minus of 0 plus 1, which is equal to minus 1. Now, A3, 1, the sign is positive, leave that round column, minus 1, 2, 0, minus 2, minus 1, 2, 0, minus 2, minus 1, 2, 0, minus 2. What is the answer? 2 minus 0, we get to 2. To take up A3, 2, the sign is negative, cofactor of 0, 1, 2, 3, minus 2, 1, 2, 3, minus 2, minus of minus 2, minus 6, answer is plus 8. A3, 3, positive, leave that round column, 1 minus 1, 3, 0, 1 minus 1, 3, 0, you will be getting 0 plus 3, it is 3. What is the cofactor of the matrix A now? Cofactor of the matrix A, 0, minus 1, minus 11, 0, 3, 1, minus 1, 2, 8, 3. What is the adjoint? Adjoint is 0, 3, 2, minus 11, 1, 8, 0, minus 1, 3. Cofactor is, if you take the transpose of matrix of cofactors, you get adjoint A. I think you have understood how to solve this problem. Given a matrix A, take out cofactors of all the 9 elements, form the cofactor matrix, then you take the transpose of the cofactor matrix. When you take the transpose of cofactor matrix, you will be getting adjoint A. I think you have understood both the problems of 3 cross 3. Find the inverse of each of the following. It is problem number 5. You have to find the inverse. Given A is equal to 2 minus 2. Sorry, 2 minus 2 and 4, 3. While finding out inverse, check whether the given matrix is singular or non-singular. That means you have to find out determinant A. 2 minus 2, 4, 3. What happens? 6 minus of minus plus 8. That's equal to 14. Determinant A is not equal to 0. Hence, what is your conclusion? A is said to be non-singular. When the matrix A is non-singular, you can find out the adjoint. So, to find adjoint, you have to take A11. What is A11? 3. What is A12? A12, sign is negative, minus 4. What is A21? Second row, first column, sign is negative. Leave that round column, you will be getting minus 2, it is 2. What is A22? Sign is positive, cofactor of 3, it is equal to 2. So, what is cofactor matrix? 3 minus 4, 2, 2. What is the adjoint? Adjoint is given by transpose of matrix of cofactors. 3, 2 minus 4, 2. Check whether it can be done directly. Interchange the diagonal elements. Change the signs of the other elements. What is A inverse now? 1 by determinant A into adjoint A. What is determinant A? Determinant A is 14. Adjoint A 3, 2 minus 4, 2. I think you have understood how to calculate A inverse. So first check whether the given matrix is singular or non-singular. If the matrix is non-singular, then only the inverse exists. Suppose if determinant A becomes 0, we conclude that the matrix is singular, hence inverse does not exist. Then you find out the adjoint. How to find out adjoint? To find the cofactors, form the cofactor matrix, then take the transpose to get the adjoint. I take up next one, 6. Minus 1, 5, minus 3, 2. We have to find out A inverse. So, why we have formula A inverse is equal to 1 by determinant A into adjoint A. What is determinant A now? Minus 1, 5, minus 3, 2. What is the answer? Minus 2 plus 15. Minus 2 minus of minus plus 15, 13 not equal to 0. Now you find out adjoint. So the matrix is non-singular. You know, A11. What is A11? Leave the row and column 2. You take A12. It is minus of minus 3 plus 3. A21. Second row first column. Sign is negative. Minus 5. A22. You leave the row and column. You will be getting minus 1. What is cofactor of the matrix A? Cofactor of the matrix A is 2, 3, minus 5, minus 1. So it can we find it out directly? So cofactor, and you write the adjoint. What is the adjoint? 2 minus 5, 3 minus 1. See, interchange the diagonal elements and change the signs of the other elements. What is A inverse now? A inverse is 1 by determinant A into adjoint of matrix A. What is determinant A? Determinant A is 13. 1 by 13 into adjoint of matrix A. What is adjoint? 2 minus 5, 3 minus 1. This is how we will find out the A inverse. I think you have understood this problem number 6. So it is finding inverse of 2 cross 2. Let us take one 3 cross 3. 7th problem. A is equal to 1, 2, 3, 0, 2, 4, 0, 0, 5. We need to find out the inverse of this matrix. So let us take the formula. A inverse is 1 by determinant A into adjoint of the matrix A. Now let us take determinant A. 1, 2, 3, 0, 2, 4, 0, 0, 5. Let us expand it along the first column. 1 into 10 minus 0. Or else you can use the formula. What is that? All the elements on one side of the diagonal are 0 means value will be product of diagonal elements. Determinant A is 10 not equal to 0. Hence matrix A is non-singular, inverse exists. Let us find out the cofactors of all elements. A11. What is A11? Plus 2, 4, 0, 5. It is 10 minus 0, 10. Let us take A12. Sign is negative. For this element, leave the row and column 0, 4, 0, 5. 0, 4, 0, 5. Answer is 0 minus 0, 0. To take up A13, sign is positive. Yes, so you want it for 3. Leave the row and column 0, 2, 0, 0. So answer is 0 minus 0, 0. Now you take up A21. Sign is minus. Leave the row and column 2, 3, 0, 5. 2, 3, 0, 5. Think you have understood. For 0, leave the row and column 2, 3 and 0, 5. You will be getting minus 10 minus 0, minus 10. To take up A22, it is plus. A22 for this element. Leave the row and column A22 and 1, 3, 0, 5. 1, 3, 0, 5. It is 5 minus 0 which is equal to 5. A23, the sign is negative. For 4, 1, 2, 0, 0. 0 minus 0, 0. I think you have understood A21. Wanted this for 2, 3, 0, 5 you get. If you evaluate you get 10. Now let us find out A31. Sign is positive. A31, 2, 3, 2, 4. 2, 3, 2, 4. 8 minus 6 which is equal to 2. A32. A32. Leave the row and column. 1, 3, 0, 4 you get. 1, 3, 0, 4 minus of 4 minus 0 minus 4. A33 you take. Sign is positive. 1, 2, 0, 2. 1, 2, 0. 2 minus 0 is equal to 2. What is the cofactor matrix? Cofactor matrix 10, 0, 0. Minus 10, 5, 0. 0, 2. 2 minus 4. It is 2. What is the adjoint? Adjoint is the transpose of matrix of cofactors. 10 minus 10, 2. 0, 5 minus 4. 0, 0 and 2. Now let us find out A inverse, which is 1 by determinant A into adjoint A. What is determinant A? Determinant A is 10 into adjoint A, 10 minus 10 2, 0, 5 minus 4, 0, 0, 2. This is what adjoint is. I think you have understood how to find out the inverse of 3 cross 3. First you find out A11, understand A11 means it is 2, 4, 0, 5. So 2 5s are 10. A12 for second element, leave the row column 0, 4, 0, 5, 0. For 3 it is 0, 2, 0, 0, it is 0. For 0 it is 2, 3, 0, 5. 2 5s are 10 minus 0, it is minus 10. For 2, leave the row column 1, 3, 0, 5. So we will be getting 5 as the answer. A23 will be for 4, 1, 2, 0, 0, it will be 0. A31, 2, 3, 2, 4, 8 minus 6, that will be 2. A32, 1, 3, 0, 4, so it will be, sign is minus, 4 minus 0, it is minus 4. A33, 1, 2, 0, 2, it is 2 minus 0, which is equal to. Form the cofactor matrix, take the adjoint, write A inverse. A inverse is 1 by determinant A into adjoint A. I think you have understood how to solve this problem. So similarly, I will give you 2 or 3 homework problems. Try to find the inverse of those matrices. So you need to solve these 3 problems at home. 1, 0, 0, 3, 3, 0, 5, 2 minus 1. Find inverse of this. Second problem, A is equal to 2, 1, 3, 4 minus 1, 0, minus 7, 2, 1. This is B. Matrix C, 1 minus 1, 2, 0, 2 minus 3, 3 minus 2, 4. Please try to solve these 3 problems. Inverse, you know how to find out the inverse. Inverse of a matrix is given by 1 by determinant A into adjoint A. Find out determinant A, that means verify whether the given matrix is singular or not. If it is singular, inverse does not exist. If it is non-singular, inverse exists. Then proceed with finding the adjoint of a matrix. So please understand these concepts, solve these problems. That's all for the day. Thank you.